Okay, good evening, ladies and gentlemen. This is Professor David J. De Los Reyes. For tonight, I will be discussing lesson number 15 on my analytic geometry long video format topic. So this is a long video format. The title of the topic is Analytic Geometry lesson number 15. And the title of the topic is Parabola Example Problems. We are done with the so-called concept of parabolas. There are two variations of parabolas. The parabola, if the vertex is at 0, 0 or at the origin, and the other variation is a parabola if the location of the vertex is actually at its K. So to illustrate the concepts, okay, let's try to bring out an example problem of a parabolic problem. Okay, let's proceed. The title of the subject matter for tonight will be Analytic Geometry Long Video Format Discussion. Okay, don't worry, for the short videos, I could bring out some parabolic example problems under the short videos. But for the long videos, this will be it. Analytic Geometry lesson number 15, parabola example problem, meaning it's the application of the concept of a parabola. Okay, I will try to read a problem. I am an electrical engineer, and the study of parabolic curves is actually very important under the study of electrical engineering, because when you reach the subject matter transmission lines, there are some parabolic curves over there. Actually, transmission lines is not a parabolic curve, but it's almost the same as a parabolic curve, because for a transmission line, there is the so-called unit weight. Unit weight per foot or per meter of the transmission line, and this has an effect on the curve of the transmission line. But for this example problem, we will assume that the curve will be a parabolic curve, because when we reach transmission line topic, actually the curve of a cable suspended between two transmission towers is not a parabolic curve. It is a catenary, C-A-T-E-N-A-R-Y, catenary. But for tonight, for simplicity of solution, as an application of the concept of parabolic concept, we will assume that the weight of the transmission line or cable is negligible, so the curve that will come out will be a parabolic curve. Okay, let's proceed. The transmission line is suspended between two towers which are 200 feet apart. We got a transmission line, we got the first tower, we got the second tower, and then between these two towers, there is a transmission line which are attached at the highest point. Okay, so this is the attachment at the highest point, and so with this one. So this is the curve of the transmission line. So I place it there. This is the red thing here is the transmission line. Okay, they are 200 feet apart. Okay, the lowest point on the line, on the transmission transmission line is 30 feet above ground. Of course, if we try to suspend the cable between two towers, there should be a curve. And for the meantime, we assume that the curve will be a parabolic if the unit weight is negligible. But just in case the unit weight is not negligible, we could not assume that the curve will be parabolic. So for simplicity of solution for tonight, just an illustration of a parabolic thing, we will assume that the unit weight of the cable will be 0. Okay. So the lowest point on the line is 30 feet above ground. The lowest point on the cable is this point here. Okay. So if this is the horizontal ground, the height of the lowest point with respect to the horizontal ground is 30 feet. Okay. Find the equation of the transmission line without considering the unit weight, or if the unit weight has no effect on the shape of the curve. Meaning, if we assume that the unit weight will be equal to 0, it's not 0, but for simplicity solution for tonight, we will assume that it will be negligible, so we could apply the concept of parabolic curve. Okay? The tower height is 180 feet. So the problem is asking what will be the equation. Okay, I will try to repeat it. We got two transmission towers. The height of the transmission tower is 180 feet. The distance between the two towers is 200 feet. So this is 100 and this is 100. Of course, if we try to suspend the cable transmission line between the two towers, the curve will be symmetrical. So the axis of the parabola will be a vertical axis, meaning the axis will be the y-axis, right? This is the axis of the parabola, because the curve will be symmetrical with respect to the left and right. So the axis is actually the y-axis. Okay, the lowest point on the transmission line is 30 feet above ground. So this is 30 feet. This is 30 feet. And the problem is just asking what will be the equation. So the requirement here is find the equation. Of course, it should be a parabolic curve. Parabolic if the unit weight of the cable is approximately equal to 0. Because when we reach transmission lines, if the unit weight of the cable is not 0, we could not assume that the curve of the transmission line will be a parabolic thing. It's a catenary. Catenary. Okay? That is, if we try to consider the unit weight, okay, we will try to consider the unit weight. It will be a catenary instead of a parabolic curve. But for simplicity of solution tonight, as just an illustration, so we could use the equation of a parabola, we will assume that the unit weight will be equal to 0. So the problem here is what will be the equation equal to? Okay? Let's try to bring out the solution. The solution will be something like this, similar to a parabolic curve if the unit weight is 0, right? So I place it here, similar, the curve of the transmission line will be a parabolic curve if the unit weight has no effect, or weight will be approximately equal to 0. Okay? We assume that it's approximately equal to 0 for simplicity of solution, so we could use a parabolic equation. And for this type of parabola, the axis will be the vertical axis. So the equation will be, it's not a parabola with vertex at 0, 0. Okay? Because if this will be our x-axis, and this will be our y-axis, obviously the vertex here is not at the origin, right? It is at the height of 30 feet with respect to the origin. So because the origin here is 0 with the location 0, 0, coordinate 0, 0. This is the origin. But the vertex is actually 30 feet above ground. So the equation will be something like an equation of a parabola which is symmetrical with respect to the y-axis, okay, opening upwards. So the equation will be this one. If you try to recall the concept of the past lessons, it will be of the form x minus h quantity square equal to 4p times the quantity y minus k. For one value of y, there will be two values of x. For one value of y, there will be a left value of x and right value of x. So it will be an x minus h quantity square. x will be a quadratic thing. There is a right hand value and a left hand value. So this is the required equation actually. Actually, this is now our answer, but it's not yet complete. Because in here, to bring out the equation, we should know the value of h. And we should know the value of k. And we should know the value of p. So there are actually three unknowns here. H is actually unknown, k is unknown, and the value of p is unknown. So if we could compute for the value of h, k, and p, we place back it here, we could solve for the equation now. But if we try to observe the figure, the location of the vertex is actually at this location here. Okay? The value of x here is actually 0. So the coordinates of the vertex, the abscissa of the vertex is actually 0. Right? 0. And what is k? K is actually this one here. The distance of the lowest point of the transmission line with respect to the ground. It's 30 feet. So actually, we now know the coordinates of the vertex. 0 and 30. Right? So we now know h. It is 0. We now know k. It is 30 feet. So to solve for the equation, we must have to compute first for the value of p. Okay? So when h is 0, this is not y. This should be k. When h is 0, k is 30 feet, that's the vertex. We get this value here, we put it here. So by using this equation here, the one I put it in front, x minus h quantity square is equal to 4p times quantity y minus k. We put the value of h to be 0 and the value of k equal to 30 feet back here. What will come out? It will be an x minus 0 quantity square equal to 4p times the quantity y minus 30. We now know h, we now know k, so the only unknown is actually p. So if we try to simplify this, am I still on camera? It will be an x square equal to 4p times the quantity y minus 30. Actually, this is our partial equation. Partial final answer. Why partial? Because for the meantime, we do not know the value of p. P, we must have to compute first for the value of p. Right? And to compute for the value of p, there should be a point on the curve in which we should know the coordinates. And where is the location of that point? At this location here. This point here, because if we try to extend the curve, it will be something like this, right? So this point here lies on the parabola, and the coordinates of this point here, the topmost part of the tower. The value of x at that location is actually 100, and the value of y at the topmost point is actually 180. So the coordinates of this point here is 100 and 180. Okay? And this point here lies on the parabola. So the x and y of this point should satisfy the equation of the parabola. So at the we are now given the partial equation, right? And since at x equal to 100 feet and y equal to 180, this abscissa and ordinate lies on the parabola. So this coordinates here should satisfy this equation. So placing the value of x to be 100 and y to be equal to 180, this will become 100 quantity square equal to 4p times the quantity y. What is y at this one? 180 minus 30 close quantity. Okay. 100 quantity square is actually 10 to the power 10,000, and this should be equal to 4p. And if we try to subtract this, 180 minus 30 will be 150. We do not have to compute for p. We can go directly to 4p. So computing for 4p, it should be 10 to the fourth over 150. And that will be 10,000, okay, over 150. And the value is actually 66.67. That's the value of 4p. So for the meantime, we now know the value of 4p. We don't have to go to the value of p, because if we know the value of p, we will just multiply that by 4 and that will be 4p. So we go directly to the value of 4p. 4p will be 66.67. So if we go back to this equation here, we could bring out the final equation of the transmission line. X squared equal to, what's the value of 4p? The computed value is 66.67 times the quantity y minus 30 plus quantity, and that will be our final answer. So the equation of the transmission line is given by this equation with the given conditions, okay, will be x squared equal to 66.67 times the quantity y minus 30. That's the equation. I'll get my eraser. Where's my eraser? Oh, that guy. Okay, I will try to erase this one. Then I will place it here. The equation of the transmission line is now given by the derived answer x squared equal to 66.67 times the quantity y minus 30. So this is now the equation of the transmission line. That's it. With the given condition, we assume that the unit weight of the transmission line is negligible. Okay, W unit weight is approximately equal to 0. Because if it is not 0, the solution will be different. It's not a parabolic solution. Like what I said, for simplicity of solution, okay, we assume that the unit weight of the transmission line will be negligible, so we could apply the concept of parabolic curve. Okay, good evening from Los Angeles. This is Professor David.